Good morning, afternoon, or evening, whatever it is in your time. I am John Augie, and I'm going over day 17, part 2 of Advent of Code. This is a really challenging one, and I want to go over just here's how I solved it, in case anybody's out there looking for inspiration. I ended up solving this entirely on my own. Very proud of that. Oftentimes, I end up looking for spoilers on Reddit or on YouTube. But let me go through what I've done here. So part one is basically create a machine, an executor that's going to execute this program, and it has three registers. There's the program. You have a program counter, and if I make this a little bit smaller, this is running through a loop until the program sort of ends, and the program is going to end here where we try to access memory that's outside of our program counter. I've stored things in a way that I'll probably change it later on, but it's a very simple match on the op code and perform some sort of operations on the register. The machine was very easy to implement. The it was a very trivial thing to do, and I got lucky and got it working right the first time. Ended up on the second for the second part having to use 64-bit registers to be able to store the numbers big enough for the extreme side of part two. But other than that, there were no changes. So for part two is really interesting because well, let me just uncomment out this. You have to sort of look at what part two is generating and glean some information from that. So in this little loop here, I am solving part two for a register. So I'm setting register A to be 0 through, we just keep counting. And we look at the output, and we're going to do some checks here, but let's, for sake of this, we're just going to print line the output, the register A and the output, and let's continue so that this is going to just do this printing. So if we look at the output here, let me paginate this. It is running the program that is for part one of the actual Advent of Code input. And it is, there are patterns that you start to see as you look at the output over time. You see that as the register A increases, we're doing sort of a binary counting here. It's not exactly like you would expect this to maybe 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but it skips. We go from 2, I'm looking at the second column here, the second column from the right, goes to 2, goes to 3. I believe the next one's 5. Yeah. So it skips to 5. I think sometimes 5 repeats. We go to 6. Except for the first two columns, the patterns in the remaining sets of outputs are sort of periodic. And there are a couple of things here. There is, how long does this program grow? And what is going to be the output? And the problem is that as you change register A, you want the output of this program to be equal to the program itself. And I can't imagine how they created the problem, but they did. And here's what we have to do. The number, the final output number is huge. You cannot brute force this. Well, you could brute force this, but it is not practical to do so. So here's what I did. And I'm sort of like just going through my thought process of what I did to solve this. So let me show you the rest of this little program here. So rather than, I need to look for those patterns. And the two patterns that I'm looking at is how often are we growing the array from 1 column to 2 column to 3 columns to 4 columns, and then really for each column, when does the number in that last column change number? And that's what this ended up giving me. So if I save and I run this, let's just run this and see what happens. So we're looking at this, and we get we have to look at this as it grows. There are numbers here that are very recognizable as being. I'm going to go ahead and stop that so that it's not eating up my CPU. These are powers of 2, 512, and I'm curious how they're incrementing. We also get a count of the register at each point that the size grows, and this grows at 8, 64, 512, 4096, and so on. And then what the count is doing is it's looking at, I believe, the very last number, and it's keeping track of how many iterations does it take before that last number is going to increment. And I'm just trying to sort of derive these numbers. And what I ended up doing, let me see if I can pull this over. Give me 1 second here. So I asked ChatGPT to do some analysis on these numbers. I gave it the sequence of numbers, and like here, 1, 8, 56, 448. This is I forget what I was doing here. 8, 64. Well, I mean, I'm going to end up using these, but I used ChatGPT just to give me what is the general formula for these numbers, and one of them is this 7 times a to the n, and the other one's going to be just like 8 to the n. And what I end up doing is using that to determine, for one, at what point are we, man, the birds out here are noisy. I don't know if you can hear that. At what point do we have the same number of output values as our input program? And that's going to be here at these even numbers here. So whatever this equation is, which if we look at our final program, ends up being 8 to the power of the exponent, and it's at the exponent here is the program length minus 1. How many output ones are there? And so that gives me a starting point. This is the starting point for my registers, and I do this assertion just to make sure that that register is going to be equal to the program length, and then like 1 minus the register is equal to the program length minus 1. Basically meaning that at that point in time for this register A, this base register value, we have, we're at the beginning of our computational cycle for that number of output values. And from that point, it is somewhat predictable. It's at least workable. So what I end up doing here, and I've left in what the general case and the case commented out that I had before for 16. I create a set of exponents, and you can actually look at it better if we print out this one here. We'll see if this will give us the information that we need. Let me comment out our this, and we're going to build this and run. So let's look at the output here. Okay, so we're starting here at this register value, and we are considering these exponents, basically knowing that we can add a certain amount to increment the very last number. Well, not exactly. We can add amount to the register based off of a formula. And that formula here is going to be this: 64 times 8 raised to a power, depending on how far into the exponent you are. And what I'm doing is I'm incrementing this very last exponent by some value. And so, we start here, and given the exponent of zeros, we get this output, and this is what our program that we're comparing it to. And what I end up doing is, you can see this, I'm incrementing this exponent until I get that very last value to match right here. This 0 and this 0 match. And when it does, I start I hold that exponent steady, and I start increasing the next exponent. So this little loop here is basically doing the binary add of the most significant digit in my output to be able to increment that value. And all I'm actually doing here in the comparison, well, that's not all I'm doing, is I'm looking at, okay, is this one right? Is this one right? Okay, we're good. We'll check the next value. Is the next one right? We're good. And if we're not good, and this is where this statement is here, we're looking at our output in reverse from right to left and finding the position of the first bad value where they don't match. And when we find a bad index, we're going to increment that exponent by 1, meaning that we know that that's not a good value. And we're also going to set all of our remaining exponents behind that to 0. We're resetting that. Long story short, what you're going to see here in our output is that our output is slowly going to converge to the same as our input program. And it actually takes a little bit of time because we have to try it doesn't always match right. The program output is not a sort of a perfect binary sequence. But it's good enough that it's not that it's good enough. It's that we find the imperfect side of it, and search for the next one that matches, because there's going to be some repetition. It's an interesting way of solving this, I think. But if you keep your eye here on this center output column, as I scroll through this, you'll see the sort of pattern of the program finding matches, and the zeros go out here further. It's finding matches. It finds a non-match and goes back and tries the next one until it finally gets everything. And you see, like here, like, we are almost entirely matched, except we're going to have to collapse down almost back down to 0 because of just the way these numbers are coming out right here. Yeah, we come back down to only matching the first 6. The very first 2 columns are kind of unpredictable. So that's why in the exponents here that I'm going to do kind of a fast way of finding it, I do everything except for the first 2 exponents. And that's because once I've potted all of the high level of exponents, I only have to check maybe a couple of hundred brute force. So we end up finding, should give you some more room on the program, this part up above finds the higher level exponents, and gets us to within a couple hundred, maybe a couple thousand. And then we just brute force the last. We just start with our register and try it and increment until we find the next one. And here's that number. I can't even fathom what that number is. It's 2 with a bunch of zeros after it, and it does it very, very quickly. In this case, it's doing it in 172 seconds because I'm storing the output. But if we run this without any printing, this should run in a couple of milliseconds. So that's my output. I don't know that you'll be able to follow this. My code's checked in on GitHub. It's publicly available. My GitHub repository is Augie, and you can look at it. This works for both the test code and for the sample program. So either they've crafted the program such that they always get the same answer on the test, or not, or we just lucked out, or there's a very predictable output for these programs. In anyway, that's my solution. I'm quite happy with it. Also very happy that I didn't look at any spoilers. I think I got lucky. But knowing, having done this this is at least the third year in a row that I've done this, you start to see these patterns where you need to look for patterns that you can mathematically represent. Okay, that's my take on this. Let me know if you have any questions. I might try to come up with a way to visualize this. Certainly, the output helps you to see that, but there's some curious ways to visualize this. So, happy coding. We only have 7 more days, depending. This is fun. This is the first kind of real challenging one that couldn't just be done with some clever coding. You had to look at the output to find patterns. So, have a great day.